All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're saying in this one, let's use our area method to draw our shear moment diagrams for our beam that we have shown. And then we're given our support reactions just to move everything along. 18 kips, 26 kips. If we're struggling to find support reactions, take a look at earlier videos. There's a bunch in there that we can work through. It's the 2D rigid body equilibrium ones. But really, all we're going to do is come in and say, let's work left to right across our beam and apply our rules. We know, for example, that if our force acts up, our shear goes up. If a force acts down, our shear immediately goes down by that amount. Either way, nothing's going to happen right there to the moment diagram. If we have a counterclockwise moment, our moment goes down immediately. If we have a clockwise, our moment will immediately go up. But nothing's going to happen to our shear. And then for distributed loads, our shear at the end of our distributed load is our shear at the beginning minus the area of our distributed load. We can use that area of our distributed loads to work with our moments. The moment at the end of a distributed load area is our moment at the start plus the area of the shear. We basically are looking at the areas one graph above where we're currently working. We're given our supports, 18, 26. Let's come in and break this into areas. So in our free body diagram, there's really one distributed load. Let's find its area. I'm going to call this area 1, A1. And I'll need to find area 1 to really get this up and going, to be able to finish my shear diagram. Area 1. Area 1's a rectangle. We can just come over to the side and get that. Area 1 should be, well, the area of a rectangle is base times height. 8 times 1.5. 8 times 1.5 is going to get us that this area is 12. In our units, we have feet for our distance, kips per foot for our distributed load, feet times kips per foot, the feet will cancel. We are left with kips for our unit, which is area of shear. But that's all the areas we need to make our shear diagram. So start at the left edge and just work left to right across this. So we're going to start here at 0. Always we should start and end these diagrams at 0. If it doesn't, something's wrong in our work. There might be something that pushes us away or back to 0, but it should be a quick check for us. But we're at 0. As I move to the left, I hit my support reaction. Should make us immediately go up 18 by the magnitude of our support reaction. So I'm now up here at 18 kips. As I keep going to the left with that, there is no distributed load. If I integrate 0, I get a constant. So I'm going to be constant 18 in this entire interval. When I get to B, I hit a 20 kip force that goes down. That force going down immediately decreases my shear diagram. So I'll drop from 18 minus 20 is going to get me to -2. -2. And there's no distributed load in this next interval, so I'm constant at -2 until I get to my next point in here. There I get a 12 kip force that goes down, so -2 minus 12 will get me to -14. And again, no distributed load over the next 10 feet, so nothing's changing our shear. We're constant until we get to D, where we have dy and a distributed load. Both show up in here. I want to resolve that concentrated force. It happens in an infinitely small distance before I deal with that distributed load. So -14 plus 26, because it's positive, we're going to go up. -14 plus 26 gets us to 12. And then our shear at the end of our interval, that'd be the end of our beam for this one, is the shear at the beginning. We'll take our last point that we plotted, so we don't want to use -14. We'll take 12 minus the area of our distributed load. 12 minus 12 gets us back down to 0. So we'll come down to 0. I had a constant, a rectangular distributed load. If I integrate a constant, I'm going to get a linear function. So I just linearly decrease from 12 back to 0. And that's my entire shear diagram. Way quicker than trying to come up with 4 equations, one for every single interval that we have in here. We can take that and just keep going. So now I need to look at my shear and say, well, let's break it up into areas. I already got an area 1, so I need to get a couple more areas. I'll have a rectangle here. This can be area 2. Area 2. Another rectangle will be 3, 4, and a triangle here. We can call area 5. So 4 more areas to calculate, and then I can again work left to right across my beam. So area 2 is a rectangle. Area of a rectangle is base times height. So 6 times 18. 6 times 18. Or this is going to get me that area 2 is 108. And our units here, if we think about that, we have kips for our height, feet for our bottom, kip times feet, or kip feet. That's a moment unit. This is why we can use that to get moment then. Area 3, also a rectangle, should be base times height. Our base is 8 times our height, -2. Base times height will get us -16 kip feet. Kip feet. Area 4 is also a rectangle. So we'll have base times height here. Base is 10, height is -14. 10 times -14 is going to get us -140. -140 kip feet. And then our last one, we have a triangle for area 5. So area 5 would be 1/2. Our base is 8, and our height is 12. 1/2, 8 times 12 will get us 48 kip feet equals 48 kip feet. And then I can just start working left to right across this. So we start at 0. There's no couple moment. Nothing's going to immediately make us jump away from that. If we did, we'd still want to put a dot right there at 0. And then I can say, well, as I move to the left, I need to resolve area 2. So my moment at the end of an area, moment at the end of area 2, is the moment at the start, 0, plus area 2, plus 108. So we're going to end up here at 108. 108. I had a constant for my shear. If I integrate a constant, I get a linear function. So this is linear. As I go to the next one, the moment at the end of area 3 is the moment at the beginning, 108, plus area 3. 108 plus a -16 will drop us down a little bit because we're adding a negative. We're going to end up at 108 minus 16 is 92. Constant shear, linear moment, so straight line, or what should look like a straight line. Then we can do that with area 4. The moment at the end of area 4 is going to be the moment at the beginning, 92, plus our distributed load. 92 minus 140 will get us all the way down here to -48. -48. And again, we have a constant function there, or a linear function, because we had a constant shear. On the last one will be our moment at the end of area 5 is the moment at the beginning of area 5 plus area 5. -48 plus 48 gets us back to 0. So we can close out our diagram. And again, let's just come through and really briefly shade this in. It just makes it look nice to shade it. That would be our entire shear and moment diagram. If we were asked, like in a later class, to use the maximum moment, we just come in and say, oh, I can read that off my graph. It's 108. The maximum shear, we need to design and make sure we could hold 18 kips. It's kind of where you go in a mechanics and materials class with that. But hopefully this is a useful video for you. If it was, stick around, watch more videos. Let's get you in A with JJ.